Thin layer chromatography, background. In this webcast, we will discuss the first organic laboratory technique that you will learn for this course. To begin, we will start with what chromatography is, and then delve more specifically into thin layer chromatography, in terms of how it works. Chromatography is a technique that separates chemical mixtures based on intermolecular interactions. In a chromatography experiment, compounds transition or move between a stationary phase and a mobile phase. The stationary phase, as the name suggests, is a fixed, non-moving, usually a solid, but it does not have to be, material that is attached to some inert, unreactive surface. The mobile phase, again as the name suggests, is a moving phase, which is a fluid, either a liquid or a gas, that flows over or through the non-moving stationary phase. Oftentimes, this mobile phase is called the eluent when referring to a specific substance or composition. Now let us talk about how these intermolecular interactions are relevant in a chromatography experiment. Why do these intermolecular interactions allow us to separate mixtures? In a chromatography experiment, the molecules in your starting mixture are in contact with both the stationary and mobile phases simultaneously. Some of the molecules in your mixture may have strong interaction with the stationary phase, while some molecules in the mixture may have weak interactions with the stationary phase. This results in partitioning. Molecules that weakly interact with the stationary phase will not stick to the stationary phase very much. As a result, they will spend a great deal of time in the mobile phase and will move quickly through the apparatus. In contrast, molecules that have a strong interaction with the stationary phase will stick well to the stationary phase and will not spend much time in the mobile phase. Therefore, they will move slowly through the apparatus. Here is a visual demonstration of a typical chromatography experiment. This green box represents our stationary phase. This is the non-moving phase which our compounds, in this case our red diamonds and our yellow triangles, are placed onto and are interacting with. The blue circles represent our mobile phase. Remember that the mobile phase flows over or through our stationary phase, shown here by the blue circles moving upward. In a chromatography experiment, some compounds may strongly interact with the stationary phase, and some may weakly interact with the stationary phase. Let us see whether compound 1, the red diamonds, or compound 2, the yellow triangles, interact with the stationary phase with different strengths. Here we are again moving the mobile phase across the stationary phase, and we can see that compound 1 has moved up the stationary phase. What this tells me is that compound 1 does not interact strongly with the stationary phase. Therefore, it enters the mobile phase and moves across the stationary phase. Now, this does not mean that compound 1 does not interact with the stationary phase at all. As you can see, compound 1 has returned to the stationary phase. In contrast, compound 2 has not moved. This means compound 2 has strong interactions with the stationary phase. This does not mean that compound 2 never moves. Let's do another cycle of our mobile phase. As you can see, both compound 1 and compound 2 have moved across the stationary phase. However, they have moved at different rates. They have partitioned themselves. Compound 1 has weak interactions with the stationary phase, therefore it moves quickly across the stationary phase. Compound 2 has strong interactions with the stationary phase, therefore it moves slowly across the stationary phase. And this is how a chromatography experiment functions. Compounds in a mixture are separated based on the strength of the interactions they possess with the stationary phase. Now let's take those ideas and apply them to a particular type of chromatography. In this case, we are discussing thin layer chromatography. Thin layer chromatography, like any chromatography technique, has a stationary phase and a mobile phase. In thin layer chromatography, the stationary phase is a thin layer of adsorbent material fixed onto an inert surface. Remember that adsorbent means that substances will adhere to the surface of the material. Here on the left, we see an example of a thin layer chromatography plate, or TLC plate for short. The stationary phase on the TLC plate is this white substance you see coating this flat surface. We will talk more about the stationary phase shortly. In a TLC experiment, the mobile phase is a solvent or mixture of solvents that is pulled across the stationary phase using capillary action. Here at the bottom of this jar is a small amount of organic solvent or a small amount of a mixture of organic solvents. When the bottom of this TLC plate is placed into the solvent is slowly drawn up the plate via capillary action. The result of the mobile phase, the eluent, being drawn up the TLC plate through capillary action is as that eluent moves up the plate, it carries analytes with it. These analytes are separated due to differences in attraction for the stationary phase. The stronger the attraction, the stronger the interactions with the stationary phase, the less distance the analytes move. In contrast, the weaker the attraction the analytes have for the stationary phase, the weaker the interactions, the farther they move up the plate. Let us look again at this example TLC plate. Before this TLC experiment was performed, at the bottom of the TLC plate here was placed a spot of black ink. If we started with black ink, how do we have all these different colors? Black ink is actually a mixture of several different organic compounds. These compounds happen to be colored. By performing this TLC experiment, we have separated the colors in that black ink, as you can see here. The colors at the bottom of the TLC plate, here on the left, had strong interactions with the stationary phase and so moved less far. In contrast, the colors at the top of the TLC plate, the yellows, the oranges, and the reds, have weak interactions with the stationary phase and thus moved farther up the TLC plate. There are three important components to any TLC experiment. The first is the type of stationary phase, the second is the type of mobile phase, and the third is the type of compound you are analyzing. To try and aid you in understanding TLC, this webcast will discuss these components separately, and it may help you when thinking through TLC problems to think about the components as separate entities and then see how they connect. We shall begin this discussion of the components of a TLC experiment by talking about the stationary phase. Remember that in a TLC experiment, the stationary phase is a non-moving, thin layer adsorbent material placed on some inert backing. There are two general types of stationary phases you can use in a TLC experiment. The first and most common type is what is called a normal phase. In a normal phase TLC, the stationary phase is a polar substance, the most common examples being silica gel or alumina. So you can see here in the image on the right, silica gel is a network of SiO-Si bonds. Each of these asterisks represents the network of SiO-Si bonds in the silica gel stationary phase. The reason that silica gel is polar is because at the surface of the silica gel, we have these silicon OH bonds, and you know that OH is a very polar bond. The second general type of stationary phase is what is called reverse phase. In a reverse phase TLC, the stationary phase is a nonpolar material. The most common example of this is silica gel that has been what we call capped with hydrocarbon chains. As you can see here on the right, we have transformed our SiOH bonds into SiO alkyl chain bonds. You know that CC and CH bonds are nonpolar. By capping OH bonds with these long alkyl chains, we create a very nonpolar surface coating. So, we have two types of stationary phases that we can use in a TLC experiment: a polar normal phase and a nonpolar reverse phase. The type of phase you use matters a great deal. An analyte's affinity for the stationary phase, or in other words, how strongly an analyte sticks to the stationary phase, depends on the polarity of the stationary phase and the functional groups in the analyte compound. Here is a general listing of common functional groups you can find on organic molecules. Here on the right, we start with standard hydrocarbons and alkyl halides, and as we go towards the left, we start seeing heteroatoms, and you might notice a trend. As we go from right to left, we go from having molecules that possess only van der Waals interactions, to molecules that possess dipole-dipole interactions, to molecules that can hydrogen bond. Do not memorize the exact order that is drawn here. Instead, remember that trend. Molecules that possess primarily van der Waals forces are the least polar. Molecules that possess dipole-dipole interactions, in other words, molecules with polar bonds, are moderately polar. And molecules that can hydrogen bond are the most polar. When we have a polar stationary phase, polar compounds interact with it more strongly. They have a higher affinity for it. They stick better. In contrast, you might imagine that if we have a non-polar stationary phase, the opposite is true. If we are using a non-polar reverse phase, then non-polar compounds should have the strongest interactions with the stationary phase. The take-home message here is that polar compounds stick better to polar stationary phases. Non-polar compounds stick better to non-polar stationary phases. The stronger the affinity of a compound for the stationary phase, the stronger a compound sticks to the stationary phase, the less distance it will travel in a TLC experiment. Now let us discuss the mobile phase. When deciding on what eluent, or in other words, what solvent or solvent mixture to use in a TLC experiment, you have to consider a few things. If we are using a normal phase TLC plate, we must ensure that our chosen solvent or solvent mixture readily dissolves our compound. Remember, in a chromatography experiment, the purpose of the mobile phase is to move or transport our analyte across the stationary phase. If our analyte cannot enter the mobile phase because it is insoluble in the mobile phase, then the analyte can never move, and therefore the experiment cannot work. The solvent we choose cannot be too polar. The reason for this is that if we choose a solvent that is too polar, all of our compounds will move too quickly and therefore will not separate. We will discuss how polarity affects how fast compounds move on the next slide. The solvent must also not be too nonpolar. If the solvent is too nonpolar, then our compounds will not move at all. Remember, these facts are true for a normal phase TLC plate. If we are using a reverse phase TLC plate, the type of eluent that causes compounds to move too quickly and the type of eluent that causes compounds to move too slowly is reversed. Generally, the eluent we choose for a TLC experiment is determined by trial and error. It is difficult to accurately predict what eluent is best to use in a TLC experiment. Here we have a listing of common organic solvents used in TLC experiments. These solvents are ordered based on their polarity, creating what we call an Eluotropic series. Eluotropic coming from the word eluent. As we go from the bottom of this list to the top of this list, we get more polar. Like with the polarity of compounds you saw a few slides back, do not memorize this list. Instead, memorize the trend. Here at the bottom, we have common hydrocarbons and other compounds that contain only van der Waals interactions. Then we have compounds that contain heteroatoms that are polar, therefore they contain dipole-dipole interactions. And finally, the most polar solvents are solvents that can hydrogen bond. This trend is exactly the same as what you saw previously. In a normal phase TLC plate, one that is polar, increasing the polarity of the eluent results in what we call an increase in eluent strength. In other words, in a normal phase TLC plate, increasing the strength of the eluent results in all compounds moving faster. The reverse is true as well. If we lower the strength of the eluent, if we make the eluent less polar, all compounds move more slowly. In a reverse phase TLC experiment, where we have a non-polar stationary phase, the opposite is true. With a non-polar stationary phase, the less polar you make the solvent, the faster the compounds move. To summarize, the more similar the eluent is to the polarity of the stationary phase, the faster the compounds move in the experiment. Polar eluents result in fast-moving compounds using a normal phase TLC plate. Non-polar eluents result in faster movement of compounds using a reverse phase TLC plate. The polarity of the eluent directly determines what we call the retention, or how far the compounds move, on the stationary phase. That is the end for the background of a TLC experiment. But before we continue, we need to be able to answer this seemingly simple question. You run a normal phase TLC plate. You then repeat that experiment, but this time you use a more polar solvent system. What kinds of compounds move further up the TLC plate? Let's break this question into components. There is the stationary phase to consider, and there is the mobile phase to consider. You know that a normal phase TLC plate is a polar stationary phase. That means polar compounds will stick well and move a small distance, whereas nonpolar compounds will not stick well and will move a greater distance. Now let's talk about the mobile phase. By increasing the polarity of the solvent, we'll increase the strength of that eluent because we are using a polar stationary phase. And we know that increasing the strength of the eluent means that all of our compounds move faster. Therefore, the answer to this question is that because we are increasing the polarity of the solvent system, we are increasing the strength of the eluent, all compounds should move farther across the TLC plate. The polarity of the compounds themselves is entirely irrelevant. The polarity of the stationary phase is what determines the order in which compounds move, or what we call elute, up a TLC plate. The mobile phase is what determines exactly how far these compounds will elute. The mobile phase will never change the order in which compounds move up a TLC plate. That brings us to the end of this webcast. To recap, thin layer chromatography is a method for the analysis of compounds or mixtures of compounds. The stationary phase of a TLC plate determines which compounds adhere more strongly to that stationary phase. The more similar the compounds in the mixture, the analytes, are to the stationary phase, the smaller the distance they travel. If you have a polar stationary phase, polar compounds adhere more strongly and therefore travel a smaller distance. If you have a nonpolar reverse phase stationary phase, then nonpolar compounds adhere more strongly and travel a smaller distance. The mobile phase used in a TLC analysis determines how far compounds travel. The more similar the mobile phase is to the stationary phase, the farther everything travels. If I have a polar stationary phase, the more polar I make the mobile phase, I make the eluent, the farther all of my compounds travel up the TLC plate. If I have a nonpolar stationary phase, the less polar I make the mobile phase, I make the eluent, the farther everything travels.